Welcome. Well, I'm going to start a minute early because our speaker told me he wants an extra couple minutes, so this way we can give him more time. Well, welcome everybody to our second lecture in the series for this season. For those of you who don't know me, I'm John Mulcahy. I'm the director of the Carnegie Observatories. Thank you. Yes. Appreciate it. It's good to have so many people, see so many people again. We have a really special treat for you today. We have really one of, I would argue, Carnegie's most distinguished scientists ever, which is saying a lot. Carnegie has been around. This is our 120th year. It's a really old organization, as many of you know, with many, many famous, particularly astronomers through the time. And I'd say Alan has really had a huge impact over the last 45 years or so. And so you get a special treat. And he's going to talk about something that everybody's interested in, of course, which is the James Webb. As I think I said last time, I can't go anywhere and say I'm an astronomer without somebody asking me about the James Webb. So it's super exciting. They've done a really great job of advertising this. So let me just tell you a little bit about Alan. He really has worked on a huge range of things, from clusters of galaxies to the birth and evolution of galaxies, supermassive black holes. He's built instruments. In fact, he built our most used instrument, IMAX, on our Magellan telescopes. Just a huge, wide range of things he's done during his career. Many distinguished awards. He got the American Astronomical Society gave him the Pierce Prize in 1983. That's given for somebody who's in the previous 5 years had done the most amazing observational work in astronomy. In 1996, he became a member of the National Academy of Sciences. He received the Public Service Medal from NASA in 1999. It's pretty impressive. And perhaps one of the most important things he did was he chaired a very important committee called HST and Beyond in 1993 to 1995. And you're going to hear a lot about this. This is a big part of the story here. But it was really that committee and Alan's work that led to the James Webb Space Telescope. And so I'll let him tell that story. He also has a very popular public book. If you haven't read it, it's called Voyage to the Great Attractor. I really highly recommend it. So all of these things you get to hear from really first, and today our story will be really firsthand from the very beginning of the James Webb to, of course, what is to come, we hope, over the next few months. And so with that, let's welcome to the stage Alan Dressler.
Thank you, John. Welcome, everybody. Good to see you in person. And with regard to the concert, now I know what I mean by a hard act to follow. We don't need that, right? Well, I've got one in my pocket, so you should be able to hear that. Can you hear me? I could put it up a little higher if it's... How about that? They have volume control up there, so they want more volume. Chief. Okay. So I've come to talk to you about some of the early days of the James Webb Space Telescope and where we are now. It's been a very exciting year for astronomers, and one that was long anticipated and somewhat feared, but it has worked out very well. I'm going to start, however, with a little bit about these things. This is a lighthouse. This is an oasis, a nursery, a metropolis, a foundry, a factory, and a cemetery. This is a galaxy. This may seem like an odd way to begin a talk about James Webb Space Telescope, but galaxies are the protagonists in this story. I wouldn't have dared to start a lecture with this kind of an introduction back when I joined Carnegie more than 40 years ago, but astronomy has changed and the world has changed with it, and somehow this isn't out of bounds now, and I'm very glad about that. But to go even further with this line, this is a home. Well, it's not our home. That's this galaxy that we live in, the Milky Way, and we're in the midst of this one, so it wraps all around. And you know, you didn't used to see pictures like this before they came out with CCD detectors in just everybody's camera, and now you can make the most exquisite pictures of the Milky Way. I wish we could see that just with our naked eye, but almost as good. Two of my favorites. So, if that's the theme of this talk, then let's spend a little time sort of setting the stage, the big picture, starting with what we see around us today, what I would call the modern universe. Galaxies are made of stars, also gas, mostly hydrogen gas. It's floating around among the stars. We're still not sure about what this dark matter is, but that's holding it all together. We won't bother to try to tell you or understand how big the galaxy is. It's just not imaginable in human terms. So, end of story. On the other hand, I was hoping that would click. Try this. Oh, that's interesting. Of course, I wasn't supposed to make the other thing go away. But there are stars, about 100 billion stars in the galaxy. And that's a big number, but it's not an inconceivable number. That's about 10 stars for every person on Earth. So maybe we can deal with that. About 10 stars for every person. Do you know where your 10 stars are tonight? I see what I have to do here. The stars are shining by nuclear fusion, and they're making the heavy chemical elements: carbon, nitrogen, oxygen, silicon, iron. And from these elements, planets are made that are orbiting almost all stars we now know. But interestingly, of course, the heavy elements in these planets, in our solar system, were not made by our sun, which is busy doing it in the inside. So these are the product of previous generations of stars. I have to get used to this, excuse me. And in general, with these 100 billion stars and the gas and the dark matter holding it all together, we see galaxies spread across the sky over an enormous vastness that, again, is unimaginable. And from our point of view, with our relatively short lifespan, this is a fairly frozen picture. We don't really see much going on when we look night from night, except for rare events like supernova, when stars explode. And that's become more important as a part of astronomy, but it's not something you just look up and see in the sky. It's a fairly quiet place, at least with your naked eye, for sure. But there are things going on, because after all, I said that this is a cradle, a nursery, a foundry, a factory, those kind of things. So stars are being born. The gas is gathered together by gravity, and it collapses into stars. Those stars age over time, and while they're shining with this nuclear stuff going on in the center, and then they die. Well, really massive stars die in a very spectacular and explosive way, and stars like the sun, which you see over here, die in a very graceful and somewhat beautiful way. But this is a process. When the stars die, they spread the heavy elements that have been made in those stars out into space, and it collects, and new generations of stars are made. So this is a continuing cycle, and it is an ecosystem. So that's what galaxies are, and now I want to make the case that they are essential for life. They're a critical step for life. In one way, it's building structure. The structure of the universe when it was very young was very smooth. This is 400,000 years after the Big Bang, when we can take a picture of what the sky looked like. So this is a map of the whole sky, like you'd see a map on a wall. And as you see, there's nothing showing there until I accidentally hit the pointer there. And now you see what it looks like thanks to microwave sensitive telescopes that we have put in orbit over the last 20 years. And this pattern of dark and light is representing fluctuations, changes in the density in the early universe, about 1 part in 100,000. So very, very small ripples that, in fact, because of gravity, gathered together and made the galaxies that we see. And this is a picture from 3 billion years later, when young galaxies have come on the scene. But they all grew out of this structure, and gravity was the only thing really at work at that time. And then in another fundamental way, so we have stars in those galaxies, and those stars have the ability to make disks of material when they're forming, and those disks become planets. So those are, to have the stars and then to have the disks that will make the planets. That's something that comes about because of galaxies. And then, as we were just saying, chemical evolution, that happens in the stars. But if there was no galaxy, there would be no vessel, no reservoir to build up the chemical elements as generation after generation of stars were born. And eventually it reaches a point, a critical threshold, where there's enough heavy material to make planets and life. So it's absolutely essential that there are galaxies, and that's why I think going back to that moment when galaxies were first being born is the critical step in our origins. It's not the Big Bang. You don't look back to the Big Bang and say, what happened there that led to us? There's a disconnect there. But when galaxies form, that's what we really would like to see, because when we began in that respect. So this is a little map of the sky, just to show you what the structure, to finish this off, the structure of the sky looks like. These are all, each dot is a galaxy. So what you see is it's not very uniform. There's a sort of a lacy appearance, and we call these filaments that make up the distribution. This is just like a pie slice, one slice. And we now understand why this was a big surprise when it was discovered in the 70s by the first time we started to make large maps of where the galaxies were, because that became possible with technology. We were puzzled by this, but it eventually became clear that this is the pattern you get when you have a very rapidly expanding universe and gravity is trying to pull things together. So it sort of shreds as it tries to do that. And that's what gives rise to this filamentary structure. And when you see a picture like this, at the nodes of these filaments is where the galaxies are born. Here's a little movie that shows that structure going from very smooth to this filamentary structure over the edge of the universe. This is what we do in computers now to simulate this whole thing. And this kind of structure that we actually see is well produced, so we think we know what we're doing. And it's the dark matter that is responsible for this growth of structure. And then galaxies form within this dark matter. And by the way, there's a little bit of a cheat here because the universe was expanding tremendously over the time that I was showing you that picture, but I can't show you that because I leave the picture. So it's expanding and collapsing at the same time, and that's what gives it that appearance. One more thing you have to know, and probably most of you do know, when you look out in space, you look back in time. It's about 2 million light years to our nearest galaxy neighbor, Andromeda. But we can see, of course, much further than that. Galaxies that are tens of millions of years back. That's still relatively recently. Look very easy to see, and hundreds of millions. And now, in recent years, we've been able to get back to billions, and that's a fair fraction of the age of the universe. I want to go back a second here. Well, the story I've just told you is made up of observations that were made starting with Hubble in 1921 when he identified that a fuzzy patch of the sky, which we now know is the Andromeda Galaxy, was indeed another galaxy. As some people have been suggesting for a long time that some of those fuzzy patches were other Milky Ways. But it was a very radical idea to think that the universe was that enormous that there were other galaxies after people had thought for so long that we were the galaxy and that was the universe. Was a truly, an ideological roadblock, something very hard for people to get their head around. But Edwin Hubble was able to accomplish that, and from that time on until the launch of the Hubble Space Telescope, for which he earned the name because of his accomplishment, a tremendous amount was learned about how stars, galaxies are related, how stellar evolution, how stars change through their lifetime, some of the things I was just telling you about. But the Hubble Space Telescope made a fantastic contribution for the last 30 years, really filling in the details of this picture. And I think I was skeptical, being a ground-based astronomer and loyal to our ground-based telescopes. I, at the beginning, did not realize what a tremendous contribution the Hubble would make. Being in space gives you a whole lot of leverage. However, the Hubble did not start out as a big success. In fact, its early struggles played a big role in part of the story that I'm come to tell you about the James Webb Space Telescope. So after the launch of the Hubble Space Telescope, a serious manufacturing defect was discovered. Its primary mirror had been polished with fantastic precision to the wrong shape, which is very interesting because, you know, precision doesn't mean accuracy. They're two different things. And it's a fascinating story. We don't have time to tell how they made that mistake, but really it comes down to this. The enormity of this project to build this telescope, again, involves sort of 10,000 people all working in their own little laboratories and factories and places to build. And there was a couple of guys who were responsible for making a test of what the mirror shape was, and it was a matter of where a lens that had been said to them had to be placed. And they forgot to take it out of the, well, they didn't know, they didn't forget. They didn't realize they had to take it out of a little brass holder. And so it went into the wrong spot by about 1 millimeter. And that's all it took to make the Hubble mirror wrong. However, so the telescope made very soft images of stars. It was very poorly focused, I mean, because the mirror was focusing light at all different places. So NASA planned a repair mission for the late 1993 that would fix the problem, a space shuttle mission with astronauts. They were going to take instruments up that had corrections in their optics so that it would cancel the effect of the mirror being wrong. But they were worried about the unprecedented difficulty of this mission, which I'll get to. In the summer of 1993, NASA informed AURA, and AURA is the association that manages, well, the National Optical Observatories, but also the new Space Telescope Science Institute that had been built to operate the Hubble Space Telescope, that fixing the Hubble was a 50-50 proposition because of the unprecedented danger to astronauts of the required spacewalks. They had never done something so dangerous. They were going to move enormous loads, which, although they didn't weigh anything, had a tremendous amount of mass, and they were going to be in space for long periods of time. It was a very difficult thing. And even the moon landing 24 years earlier did not have such difficulty or danger. And so they, as I was told at the time, were saying, if we get up there and this is really endangering anybody, we're calling it off. So the AURA board, I'm jumping the gun there. The AURA board said we need to have some sort of a study about what might happen if the worst happens. What would we be doing with, the Hubble will probably be around for a couple of years in its present state, but it's not going to have the long life we thought it would. And it took so long to build this, we better get started on a backup plan. And so they asked me to form a committee, and we together selected about 20 astronomers and sort of got to work about thinking about the situation. But it was months before the repair mission was supposed to happen in December of 1993. Fortunately, by the time our committee's work was in full swing, NASA's repair mission was a resounding success, ushering in this amazing wonder, excitement, and popularity that was unprecedented for a science instrument, and I think it made the Hubble Space Telescope, that was the beginning of its most successful science program in history. When John and I were talking about this, when we first was talking about this, in fact, for many years, people in the audience all experienced this when the Hubble went up and started taking these amazing pictures that I'm giving you some examples here. But now it's been so long in the building of the James Webb Space Telescope that there are a lot of people, I hope, in the audience who didn't actually live through this. Well, the excitement of the public all around the world was astonishing and unexpected. Most people had lost interest in NASA since the moon landings, and for 20 years NASA had been struggling to regain public enthusiasm for the space program. Suddenly, they had it. The ridicule that the flawed Hubble Space Telescope had gotten from the press and from television, it was brutal, was forgotten quickly, and NASA was so anxious to capitalize on Hubble's popularity and to see what might come next. The door was flung wide open for my HST and Beyond committee. I want to add that astronomers had pictures of these things for decades, but not with this exquisite detail and not in color. And that made all the difference. It really did, even to astronomers. People saw these Hubble pictures, and they just knew that this was not the work of artists with Photoshop. These were real things, magnificent constructs of the cosmos, and amazing. So the pictures you see here, these are all creatures of the Milky Way having to do with star birth and star death and such. But it was just as exciting for astronomers like me, who study galaxies. For the nearby galaxies, again, we had this exquisite detail that we could see what was going on when stars are being formed in other galaxies and compare them to our own and see a much wider range of conditions and learn how the process begins and what motivates it, what keeps it going, things like that. But not just on nearby galaxies. The Hubble was so exquisite in its ability to show detail that we could look back in space, in time, to much more distant galaxies and see, again, great detail. This picture down here is of a cluster of galaxies, a very rich one, 2 billion light years away. So it's looking back 2 billion years, and yet, I can't blow it up enough for you to see it, but the detail, even in these little galaxies, is pretty astonishing. We never had anything like that. I mean, we took a picture with a photographic plate on a telescope, and even then with a CCD, the atmosphere from Earth is just too turbulent, and we would get, little dots. And we learned a lot from those dots, especially when you took spectra, but seeing them as galaxies at an earlier time was truly amazing. But the big payoff was maybe a year later, I think it was 96, 97. An area was picked in the sky in which the ground-based telescopes showed no galaxies at all. Just a blank area sky, lots of that. And they took the Hubble and pointed it at that area and basically opened the shutter for 3 weeks and accumulated the light. And out came this picture where it was full of galaxies, covered with galaxies. Everything else, everything in this picture essentially is a galaxy. So we were seeing back through time to really early times. And I think my committee realized immediately that this was going to be something truly new, that we could see further and in greater clarity than we could ever have imagined and sort of ever dreamed of. So I've extracted from a later version of this Hubble Deep Field what that whole thing is about by taking pictures of, I know where these galaxies, how far away they are, so I've sort of lined them up so you can see how the universe changes. So here's today. These are some galaxies today that are in this picture, and they're sort of 13 billion years old. That's the present age of the universe. 10 billion years old, that's still relatively close. That cluster of galaxies I just showed you is sort of in that ballpark. When you get to half the age of the universe, you still see galaxies that we're pretty familiar with, and those are much younger, half the age. But when you get down here to about 4 billion years, you see they start to look different. I'm sorry I don't have more such images, but maybe you see they're little twisty shapes and blobby things, and they begin to lose this regularity that we see in galaxies today. And what is going on is that you're seeing galaxies when they were first being made. Well, the HST and Beyond Committee recognized the huge implication of what the Hubble had done. We could imagine seeing back to the origins of modern universe, our origins, by seeing galaxies being born. And think about it, that is something a civilization gets to do once. The trouble was that we couldn't see that with the Hubble, and we knew why. It's because, gee, what happened to the redshift thing? Oh, I didn't even make it. So this just shows you the effect of light redshifting because the universe is expanding, and the further away you look, the expansion causes the light to shift into the red. And the reason the view got bad for Hubble was the light had shifted into the infrared, and Hubble was not a good infrared telescope. And why is that? It is because to see first light, and that's what we've been calling that from this time, first light being the galaxies, the faintest galaxies, Hubble is blinded by its own infrared glow, and that's because the Hubble is a warm, room temperature machine. At room temperature, everything grows brightly in the infrared. Here's a picture of the zoo of two giraffes, and here's what it looks like at night. You can go take a look, and you can see the giraffe. They're probably sleeping, but you see how different it looks. They're emitting their own light. Well, the Hubble is, in fact, at room temperature, and that sounds crazy. It's in space. Why isn't it cold? Well, you see the reason. The Earth is right there. It sees the Earth in half its field of view, and it comes to equilibrium. It has the same temperature as the Earth, and so it glows brightly in the infrared just like the giraffes, and there's absolutely no possibility of seeing the light from these extremely distant galaxies as long as your telescope is glowing in the infrared. And by the way, infrared light provides a very different and enlightening view of many things in the sky, not just this ability to look back into the past. But you can see here, that these regions that are very dusty, where stars are being born, when you look in the infrared, the light penetrates the dust, and you can learn all about the galaxies that are just being, these stars that are just being born. So, the HST and Beyond Committee decided the first goal is the detailed study of the birth and the evolution of normal galaxies such as our Milky Way galaxy. And we said NASA should build a space telescope with a mirror at least 4 meters, the Hubble was 2.5, or larger, that is optimized for imaging and spectroscopy in the infrared, and that's to see first light. However, we were very greedy. We saw that this was a real moment. We decided we would catch the wave of Hubble's success and embrace not only the opportunity to see back to the beginning of galaxies, and to use the Hubble Space Telescope to fill in the evolution of galaxies up until today. We have one full picture from beginning to now. But we pushed further into human origins by adding the search for planets and life around neighboring stars, goals that we knew would last well into the 21st century. At the rate it's going, it might be 22nd, but that's just because it takes a long time to do these things. But at any rate, it is a complete program. By adding Earth-like planets around other stars and looking for signs of life, we are going from sort of the alpha to the omega, the formation of galaxies that makes it possible to have planets, and then looking for those planets and seeing how often we see signs of life, signs of water, signs of living things, and maybe someday signs of intelligent life. Who knows? So that's a program that we came up with. But by the way, I should add that this idea about, we actually said it was just the third part of it would have to be a technology demonstration, because there was nothing available that you could build at that point that could see a little planet next to a bright star. It's about 1 billion times brighter than that planet. And it called for something at that time called interferometry, which you could build a telescope out of many far-flung pieces, and you could accomplish what I was just saying about separating the galaxy, galaxies are on my mind, the planets from their stars. But now, actually 20 years later, it has been decided that, in fact, a much bigger telescope than even the James Webb could do this in the optical with a certain kind of attachment called a coronagraph. And I'm happy to say that this third goal of our committee has finally become the top priority. There was just another decadal survey, 2020, and this received the top ranking. However, it's a concept at this point. We don't know how it actually would be built, and the engineering really has to be done for many years to get to the point where it would be ready to go. So these goals were inspiring, but also I think the HST and Beyond report brought a new approach to advocating for our science, and I think this was a contribution as much as the science. We considered the questions of our motivations as scientists, relevance of our work to the society that supports it, and the nature of the fundamental questions that have driven human explorers for millennia. And I wanted to read you just a bit of the beginning to get the idea. Our other quest is as old as civilization, perhaps as old as our species. Comparing the ancient myths of many peoples tells us that the question, where did we come from, is one as cogent and profound as we can pose. For an answer, we have continually looked to the sky, the great unknown that has always figured prominently in human ideas of origins and destinies. A remarkable triumph of 20th century astronomy is the demonstration that this notion is true. Our origins, and perhaps our destiny, lies among the stars. This idea has already captured the imagination of perhaps 1 billion people. Many have not found it easy to follow our scientific findings, but very few have missed the point. The realization is probably why we find so many modern tales linked to space, a trip to the bookstore, or a glance at a movie listing or television schedule is enough to convince any of us that increasingly great themes of human existence are being projected into space. Our physical journeys into the cosmos may be generations into the future, but our minds are already in the space age. NASA responded very positively, as did our colleagues, to this report. It was something sort of different, but it also had an inspiring scientific message, and NASA responded by wanting to get it work right away. That was actually a problem with that because we run everything through decadal surveys, and that one was several years off. But there was plenty of technology to work on, so they did that. But in the meantime, they set up an origins branch of the astrophysics effort at NASA, and I had the honor of being chair of that for the first 5 or 6 years. And it used that framework to think about astronomy. Were these missions contributing to our understanding of where we came from? And it has become a big part of what NASA does. So how do we reach all the way to galaxy birth? We have to go really cold. That's the problem with the Hubble Space Telescope. We have to get something that's very, very cold. So this is a new kind of telescope. It's large, it's open, it's deployable, it's cryogenic, it's very powerful. It has 50 times the mirror area of the Hubble, and mirror area is the key to how much light you can gather. 7 times the resolution. That's pretty impressive, of the Hubble Space Telescope. You can see that it is sort of out in the breeze, so to speak, and the real challenge turned out 2 challenges. One is this telescope would be much bigger than any rocket could launch, which I will show you. But it also had to be very, very cold. And it couldn't therefore be near the Earth, or it couldn't see the sun, or any of this, or even the moon, because the light coming from those objects would heat it up to where, well, it might not be room temperature, but it wouldn't be as cold as it needed to be. So NASA decided that it could solve this problem by building a sun shield, like a big umbrella, that they could point to block out those things. And I will tell you a little bit more about this, but the important thing, I guess, is how it works and where it sits. So the sun shield is made of 5 separate layers of a sort of plastic coated with metal, very thin. And the reason you need so many layers is you're going to put it, let me go forward a little bit. You're going to put this beyond the Earth, 1 million miles further out in space than we are. We're 93 million miles from the sun, 1 more million, this is not to scale. And you're going to follow around the sun, sort of always behind the Earth like that. And you'll put this sun shield to your backside and block out the sun, the Earth, the moon. They're always back there, and the telescope is always looking out. So this is the dark side of the sun shield, and then there's a picture of the bright side. So you can see how big this thing is. It was really, they had the idea, they sort of did the concept very early on, and then because of funding problems, there wasn't really enough to build the telescope in the sequence of things that it needed to do. There wasn't enough money to do everything, so they deferred some things. And one of the things they deferred was this sun shield. And that was a mistake because it turned out that the idea was sound, but to make a structure which is the size of a tennis court out of this very delicate material, be able to fold it up to get into the rocket, which you will see, and then have it all deployed perfectly, because if there were rips, if there was part that didn't deploy, just that amount of light getting through would heat the telescope and basically destroy the whole point of the mission. I think that began to really sink in as the telescope was being finished. The last thing that was supposed to happen is it was finished at Goddard, the telescope, the scientific instruments, and then it was flown to Northrop Grumman here in Southern California, and they were supposed to take 6 months to finish up the sun shield and then ready it for launch. That and what's so-called spacecraft. And it didn't happen. I mean, it turned out that they realized at this point that it was much harder than they thought. And at this point, the investment in the telescope was so great, it was a sort of self-fulfilling prophecy that it got more and more expensive, because the more expensive it got, the more important it was that it worked. It makes sense, but it may not be the best way to do things in the future. And I think we've learned a lot from this experience. At any rate, I can report to you, this is the bright side that is facing the sun, and this is what's called the spacecraft. It's all the, we're supplying electricity and other things to the instruments, but it's all the things that really have to be warm. And believe me, this is really an amazing accomplishment to have everything on this side operating at these, I guess I didn't tell you what the temperature was. It was on that chart, and I just didn't. The cold side has to be less than 50 degrees Kelvin. That's absolute temperature scale, which is 370 degrees Fahrenheit below 0 Fahrenheit. That's pretty cold. And guess what? Here it is done. I shall show you. Oh, it's pretty hard to see, isn't it? Well, actually, you've got a better view of it than I do. So you see here, this is a page called Where's Webb? When it was being launched and going out to where it's now sitting, you could find out where it was and how fast it was moving. And now you can see the temperatures of all parts of the spacecraft, and you can see over there that the bright side has temperature of 123 degrees, sort of 57 degrees, positive sort of temperatures. These are all in Fahrenheit, I guess. Yeah, so sort of room temperature again, even though it's a million miles from Earth. And the cold side, minus 384, 393. These are some of the instruments that are in the package. They're all in the minus 400 range. So it works. The sun shield deployed perfectly. And it took months to reach this temperature because there's a lot of heat that went with this spacecraft. And it radiated away to space on the cold side, but that took a lot of time. And so we all watched that, and it was really exciting. And the other thing that was done during the same period of time while it was cooling off was the mirrors. There are 18 mirrors that are sort of yay big, and they all had to be aligned, obviously, to focus at the same point. That's not so hard, but in order for them to function like one mirror, a light wave had to hit them at the same point and bounce back. So that's called phasing the mirrors. They all had to be in the right position along a curve to wavelengths of light. So they had sensors and actuators, little piezo crystals that would be able to accomplish this, but it took a long time. It took sort of months to move the mirrors and to carefully keep checking to see when they could get them all together. And eventually they did, and they got basically the perfect images that had been planned for the telescope. And I can't show you because they're all embargoed, but you'll see them soon, I think. But for those of us, sort of, I'm on an instrument team, so I get to see them. It's very exciting to see that it's actually worked, and it really has actually worked. So let me actually show you some things from, how are we doing? Okay. Let's see if I can get this to work. After so many, I was on the phone telecon every month for, 12 years or something, 10 years. As we discussed, how the budget was going and the construction, it was so wonderful. I got a chance to see it when it was at Goddard, the telescope, before it had been shipped out to the West Coast. I'm sorry. And this is when it was at Northrop Grumman, just recently, maybe a year ago, when it was finally finished. There's that sun shield. You can see how it was sort of wrapped up and now unfolded. And then the other thing that TRW, who had originally gotten the contract, came up with was the idea of folding the mirror instead of trying to piece it together and assemble it on orbit, which sounded like a nightmare. They just folded it like the proverbial, coffee table. And that way, if they failed to deploy the wings of the telescope, they still have most of the mirror, which was pretty smart. Anyway, that's how it looked before it was finally packaged up and sent off. So as I said, the problem is that there is nowhere bigger fairing than, what is this, 1.7 meters, so it's 4.5 feet. Sorry, 17 meters. It's about 4.5 meters. I'm confused. 17 meters long. It is about 4.5 meters across. So what is that? That's 13 feet, 14 feet. So this whole telescope had to be folded origami style into this capsule. And they did it by, as we said, folding the sun shield elaborately, and you'll get to see a little picture of that. And the telescope, and everything had to be folded and put into this rocket. I hope some of you got to watch the launch, but I can play it again anyway. Are you going to do it? Well, the other one worked. Let's see. Open the movie. Oh, I'm not supposed to be connected to the internet. Well, that's disappointing. Well, that one worked. Well, I guess we'll have to pass on that. This is the telescope. This is a simulation of what it would do to deploy. You just saw the solar panels come out. That's extremely important. That provides all the power for it. This is one of the sides of the sun shield, how it was folded up, coming out in both ways. And then you'll see how it deploys a truss to unfold it, roll things out, and eventually sort of pop the panels apart. And now they separate the telescope from this brighter, warmer side. Then they began to unroll this wrap of 5 layers. Little pieces, they had to cover every square inch that was going to let light and heat in from the other side. And then they had an elaborate dance where they sort of walked it around and layer by layer unfolded it. And the reason you need all those layers is because the light is intense and the coating of metal on it is not dark enough to get rid of 99.9% of the light, which is what you have to do. So the best way to do that is to do it in 5 layers each one, which probably has a 99% transmission. But you need all 5 of them, and that's why they were worried about layers that didn't separate, layers that might rip, things like that. But again, I'm very happy to say all this has come to pass, and there is a fully functional telescope out there. And now we're working on getting the instruments working. And I just can't get used to the idea this isn't going to play. Why is it not doing this for me? Yeah, let's see if I can do that. Open movie in browser. Okay, let's try this. Open movie in browser. I'm not connected to the internet. It's got me coming and going. Let's see. Well, let's see what happens if I go back to PowerPoint and that little thing will stay there. Open movie advisor. Sorry, playback of this online movie is not currently supported. It was supported an hour ago. And I don't think it'll let me do it the way it was showing. Well, that's really surprising. I did this yesterday and it worked well. So moving on. Yeah, okay, I got you here. Now we go back. So, another movie. So now this is the telescope actually moving away from the Ariane. I'm sorry you didn't get to see the launch. Maybe this won't work either. The mysteries of PowerPoint. I'm not connected to the internet. Maybe that's the problem. I'm not supposed to need to be connected to the internet, but let's see. I can't do that. All right, I admit defeat. Wait. Hey. Why did that work? I have no idea. All right, the launch of the Ariane rocket, the French Guiana, and it was... I hope you can all count backwards from 10 in French. Oh, how is that possible? Sorry. All right, we're going to get through this. Let's see.
And we have engine start.
Well,
And lift off.
so the other one is there, huh?
Punching a hole through.
Boy. Okay. Yeah, but now it's not going to play. Bummer. Serious bummer. Well, okay, we got this one at least. So, launched away from launched away from the Ariane, the James Webb Space Telescope in its final performance, the last we'll ever see of it. But if you watch carefully in the lower left, you will see the solar panels deploy. It was 30 seconds after it was let go from the rocket, and everybody held their breath because if this one thing had failed, there was no way to recover from it, and without any power, it would have been dead. But just about at this point, maybe the video will fail. Oh, boy. All right. And it worked. And as somebody pointed out, this is the last we'll ever see of it. This is the last few humans will ever get of this telescope, at least for the foreseeable future. I wondered to my wife at the point, why didn't they put cameras on this so we could see all the subsequent things? And then I found out. So if anybody wants to ask the question, I will tell you. There was a good reason they didn't. There was a good reason they didn't. Well, we have to kind of move along. So I just want to sort of finish up with a little bit about the instrumentation and such. There are three major instruments. On the James Webb, a camera that images a fairly decent piece of the sky, like the Hubble did. A spectrograph, which can take many objects and take the spectra in the infrared again. And a far further infrared camera and spectrograph that is meant to look at even more shrouded kind of things. I'm a member of this NIRCam team led by Marcia Ricci at the University of Arizona, and we have a joint collaboration with people in NIRSpec to do some of this early galaxy, Earth and galaxy work of first light. Much as the Hubble deep fields dominated the field of galaxy evolution, galaxy growth, the NIRCam team deep fields will focus on areas extensively already studied by Hubble, but in the infrared. So we will see those things it couldn't. The program requires 300 hours of observing time from the sort of 400 hours that were granted to the NIRCam team in acknowledgement of a decade more, actually, of very challenging and difficult dedicated work, which I did not participate, but many people did. These first fields are not going to reach the ultimate depth, but they're going to get orders of magnitude fainter than we've ever seen before. So what are the basic questions? What do the first galaxies look like? How did their numbers and masses grow? That's the beginning of galaxies. How did they make stars and grow to what we see much later? And the real question is, how did this crowded, gas-rich environment at the very beginning, things were almost all gas, and sort of explosive in that regard, because there was all that fuel for stars to form from. And we expect that to have been a very dynamic period of the universe. In particular, galaxies were very crowded together, and so they probably were bashing into each other a lot. Let me show you again from this. This is the 4 billion year picture that we saw with the Hubble, and saw these twisty-looking things, and then sort of nothing here at the next layout. But this is an example of what we see today when galaxies collide. And you see some pretty amazing things, and some rather explosive things if there's enough gas involved, because the gas kind of bangs together and reacts. But more to the point, here are some of these more distant things, and maybe we'll see things like this, but we won't know until we see these things and make measurements of them whether they will turn into galaxies like a spiral or a galaxy like this elliptical galaxy, very different sort of things. And it's going to take a lot of patience and a lot of measurements of what do they look like and what are the spectra that show where the stars are forming to sort it all out. This camera, the NIRCam, is actually made of 4 sets of detectors like that. These are very amazing infrared detectors, and you get more area by building them together like that. And then there are 2 sides of the camera. You split the infrared band into a near and a far, and therefore you can get more detail. You can do it in 2 colors at once. And also the camera is back to back, the same thing. So there's actually 2 of these, and that's good both because you've doubled the area that you can work on in the sky, but also if one of them fails, you have a camera and you can go on. This is the entire instrument package. I've never seen anything that really looked like this. It's got to be one of the most complicated things ever built. And the NIRCam is wedged in here, and these are the other instruments. So I'm going to finish up at least this part of it, and we can go to the questions, just by quickly saying something that may be a little hard to follow. But the idea about looking for the galaxies growing is to see what kind of stars they have and map how the stars were formed in that early period. And what this little plot here shows, and I know it's kind of verboten to show any plots, but this is color on this axis, just like you see here, like a rainbow, going from the optical all the way out into light in the ultraviolet you can't see with your eyes. And really young stars are very, very blue, or very ultraviolet. That's what it means with this really blue light. And as you see, stars that are older, sort of 100 million years, are still very, a lot of ultraviolet light, more than anything else. But down here are all the old stars, 1 billion years, 2, 3, 4, and they all have about the same shape, and they're all very similar looking. This has always been a problem for us in studying galaxies and how they were forming stars, because anything that was between a couple billion years old and 10 billion, they all look alike in their spectra, so we can't tell them apart. But now we'll be looking at a period of time when the whole universe is only a billion and a half years old. So there won't be old stars that cannot be held from one another. We will see only things that change very rapidly. This is a little cartoon here showing you that the spectrum, that is the rainbow for a young stellar population, looks very different than one for a intermediate age, and then all these red lines where they no discrimination. So I have a program that will take the light from the NIRCam. So now you have another thing too. Again, we have color on this axis, and these are actually the wavelengths of infrared light. And at each point is a color in the infrared that NIRCam will take a picture in. So, and this is the intensity on this axis. So it says, this is what the rainbow looks like in the infrared, these points. And I think it went backwards. So, I have written a program that can take, using this information of what young stars look like at different ages, and to take and make such a spectrum until I get it to match. What kind of stars did I have to put in? How many at 500,000 years? And add them all up. And to test that now, I'm in the process of making, I don't have the data yet, but I have to be ready for it. So I'm making models by making up my own star formation histories. That's what this little thing is over here. So you see these little blue sort of thing. That's my made up star formation history. This is the numbers of stars per year that are sort of been making. So it starts out low. There's a big burst of star formation according to this random model, and then it goes down, and then there's another burst, and that's pretty much it. And the green squares are what my program recovered, and it's not bad. It found those two bursts, and it recognized them. So that means that if we see such a thing, I will be able to say this galaxy had a burst, and then another burst, which might be indicative of a very violent sort of collision between two little galaxies, and it sort of explosively took off, or something we call feedback. It could be that the first burst was so energetic it threw the gas out into space and then it came back. We don't know. I really don't know what galaxies are like. But just to show you a very calm example, here's the spectrum, the colors, which is very different looking, for this star formation history. This is what the data would look like. And these points here show pretty much a constant star formation. And although it's not perfect, that's kind of what I recover. So I'm in the middle of an extensive sort of modeling of this kind of thing. You look at them from different ages, and you look for different histories, and you have to sort it all out. It's complicated, but I seem to be making good progress. And that's one of the things that will be done. Wish I could tell you more. Well, some things that are takeaways. The Hubble Space Telescope took us to the threshold of galaxy birth, but we need this big super cold James Webb Space Telescope to reveal the infant galaxies whose infrared shifted light comes to us very faintly from the beginning of the modern universe. The cradles of galaxy birth are not going to give up their secrets easily, but histories of star formation should be easier to unravel when all of the stars are young and their spectra change rapidly to reflect their recent histories of making stars, and that'll tell us how did they build. At the centennial of the discovery of galaxies in 1921, on Mount Wilson Observatories, the James Webb Space Telescope and its likely successor, an even larger telescope that will specialize in discovering Earth-like worlds in our corner of the Milky Way, should, by mid-century, I would hope, resolve these age-old puzzles about key steps in the origins of life on Earth and our own. Thank you.
I'll remind people we have mics on the two sides. If you'd like to come up and ask your questions, please do that. We also may have some online questions. Oh, wait, your video's... Hey!
There's, yeah, it's going to go. Okay, so you heard it. You just didn't get to see it. I mean, what's wrong? So it's sitting there ready. This is in French Guiana in South America. I had been told when all this started that I would get to see the launch of the Space Telescope, but then they completely reneged on that. They're counting backwards in French.
3, 2, unité, top.
Some great pictures, though.
And we have engine start. And liftoff. Décollage, liftoff from a tropical rainforest.
Were you watching live?
Yep.
My wife and I, Charmaine, we were watching. It was very tense, but I was confident. Sort of.
Program reported.
And I guess I should emphasize at the end, everything in this last few months, a very careful program was outlined about what to do day by day, week by week, and they have stayed on schedule and everything has worked. And so far, we're now into the point of checking out the individual instruments, but we have a fully functional telescope, and it looks very promising. And the mission, which was supposed to be maybe 5 or 10 years by the amount of propellant you could have to keep this place in orbit, is now going to be much more because of the way they watched it so precisely. And so it has enough fuel for a 20-year mission. And by God, we may need that. Sorry, back to the questions.
No, that's great. Excellent. Can you go to the mic right next to you, sir? If you can't get out easily.
Speak really loudly.
That's probably okay.
Why French Guiana?
Why French Guiana?
And why so cloudy today?
Yeah, I saw the forecast and said thunderstorms every day, and I thought they're not going to go. And French Guiana, because there was a partnership made, the Europeans and NASA together, and the Canadians all collaborated on this telescope, and one of the French have a very good rocket, and that was their major contribution. So their launch site, they don't have any place in France to do this. It has to be near the equator, and I think that's been a colony of France for a long time. There are monkeys around, and it's very, and really there's very little in the way of infrastructure there. That's why I don't think any astronomers went. They couldn't.
Who is James Webb, and why was the telescope named after him? Was he a famous scientist like Edwin Hubble?
No, he wasn't, and astronomers had a sort of very negative reaction when they first heard that NASA was going to name it for James Webb. But it was an appropriate thing to do because he was a NASA administrator during the time of the Apollo program. So you might think that would be his, great credit for something that lives on forever. But in fact, he was the strongest proponent of science. There is nothing about science in the NASA charter. It was not meant to be a science agency. And they dabbled in science for the first sort of 20 years. But it was James Webb who said, I believe, I didn't make this up, that space exploration without science is just tourism. So he really, I think, is sort of a hero to scientists because he didn't have the background that you would have predicted that he would have felt so strongly, but he did. And so it was named for him, and I think after we all realized that, it was good with me.
Excellent. We have a couple online questions, and then can I have you guys?
Can I just ask one really loud?
Where are you?
When do you expect to get photos first, or what's the timeline?
Yeah, they actually released a schedule now that tell us when the very first, there's a set of programs called early release observations, which they did with Hubble as well, where they try to get some pictures out, in particular to the public. And now I get the impression that they feel they could schedule those maybe end of June, beginning of July, that start doing work and be able to release things. So I think July is probably the month when we'll start seeing things. Hope so.
A related question, Alan, from online is, when will you get your first data?
Yeah, I don't think that's coming until, I think the schedule is like the end of the year. Just
when will he get his first data?
the NIRCam observations, which will be spread over actually a couple of years, but the first ones that we'll have to operate on what I want to do on it will probably be December or something. It's quite a long way off.
Get you wait a little bit longer. I'll get you a second. I have a guy back here.
Your own question, why no cameras?
Oh yeah, why no question? Why no cameras is the question.
Well, I asked somebody who knew about things like that, and he said they did consider it because, gee, it was a lot of stuff that could have watched. But remember that the whole point of this was to get something absolutely dark and cold, in which no other light or energy could get in. And they were worried that if they mounted a bunch of cameras, first of all, they were worried they could make a camera sensitive enough to see when there's no light. It's dark on that side, right? So, but if they could, they thought, that might be a very special camera, and maybe it'll short circuit, maybe it'll give off heat, maybe it'll malfunction, and the whole mission would go up because you wanted to see a picture. Yeah. So they decided it weren't worth it. I think there was a woman down in the front too.
There was.
to have access to that information? Which countries are going to have access to that?
You know, NASA is very proactive about this now. It isn't long before everybody has access. There used to be sort of long periods of time when the people who took the data could make exclusive use of it. But those things are down to sort of 6 months, a year, and some are immediate. A lot of things that are done are immediately released to everybody. So it's worldwide. It won't be based, despite the fact that not everybody in the world, you know, put in the cash, it's for everybody. It's a worldwide project.
So we have somebody at the mic over there.
Yeah, thank you for your work. You had a few slides back some basic questions that the James Webb is going to be looking to answer, such as what were the galaxies like at the beginning of the universe, and how did they grow, and how did they affect today's galaxies? Do you have a hypothesis on the answer to those questions?
What am I expecting? I kind of leaning toward this rather violent, turbulent time when galaxies were trying to assemble, but they were sort of releasing so much energy when for me, the key is that there was so much gas around relative to the amount of stars, which is not the way it is today, that stars will really want to form rapidly. And when that happens, a lot of supernovae go off. They inject, you saw what one supernova looks like. Well, if you get 1,000 supernovae in a short period of time, tremendous amount of energy gets released into the galaxy, enough to stop star formation for a while, because you sort of blast this stuff out and heat it up. It's too hot to cool to make stars. So I'm expecting that, but short of that, it isn't clear. People for a long time have been saying there's going to be a big burst and then a slow decline, because you see that later in the universe. And others say, no, it's going to rise rapidly and then, you know, then sort of turn up. So I think nobody knows, but my bet is on the sort of bursty
Thanks.
hypothesis. We'll see. I'll change my mind if I come back and talk about it, and that's that.
Yeah, thank you. I'm just wondering, the mirrors that are reflecting the light, are they different than what was on Hubble because they're reflecting infrared instead of visible?
Yes, the coating is gold, because gold, in fact, is much more reflective in infrared. It's like 99%, very, very good. It doesn't look so good to us, but it is. The other thing is very different about them is, again, I can't emphasize too much how hard it is to build something that's going to operate at 50 degrees above absolute zero. So the mirrors couldn't even be made of glass, because glass would not, you couldn't polish the glass to a shape that when you lowered its temperature on orbit to 50 degrees above absolute zero, it would have the right shape. So they wound up choosing a material called beryllium, which is one of the elements, and you can polish that. It comes in a crystalline form. And that's what they made each of those segments out of. And that was a complete new, I would say maybe risky direction they had to go. Interestingly enough, it was so successful, the mirrors were ready in 2012, 2013. They coated them and put them in boxes, you know, and things like that. But again, you know, it's making all of them as perfect segments of a parabola that is the whole shape, and then putting them together and tweaking them so they're all just like, it's a phenomenal accomplishment. And you know, I said this in the abstract, but I didn't realize it. Literally 10,000 people worked on this for the last 10 years. And one cannot overstate the accomplishment of getting that many people to work together, you know, constructively on something with that long a development and a payoff, and with so much risk. And I think it's a lesson that human beings are really capable of that, even though we don't often take advantage of it.
We do 2 more questions, gentlemen there, and then I will.
You have these 18 beautiful, incredibly precise mirrors, gold-plated. I remember seeing one of the early images, the first live images, of 18 crisp images of the same star. I'm wondering what algorithm you used to bring it all into alignment. Was it automated or controlled
Yeah.
on the ground?
Yeah, the first thing they did, they were all over the place. So the first thing they had to do was get them close enough so they would all appear on one image. And once they did that, they did the thing that they do with the Keck telescope, which has multi-mirrors, and that is you wiggle one and see which spot moves. And then, you figure out, well, it moved that much and I'd like it to go here. That's the center point. So I'll go ahead and I'll run that one, and then you do another one. And eventually, you have to start thinking about them all together, but because when you move that one, then it changes the other ones a little bit. But they went through that period pretty fast. And then the issue about, okay, now they're basically functioning like 18 separate small mirrors, which is not what the idea was. And now we have to adjust them so that it's if they're one piece of beryllium mirror and smooth over that thing to a wavelength of light, which is 100 nanometers, microns. They did it.
Did you still have a question like this? Go ahead.
Yeah, I was wondering, we hear about Earth-based telescopes, and people ask for time, and they get small bits. Is the same thing going to be true here, or is there a grand plan for what you're going to do for the next 5 or 10 years?
No, it's this one is pretty much not restricted. It's open for complete competition. There will probably be some projects that will have a survey that everybody can use, so the institute will make that survey and then release it immediately. And there will be a committee that probably decide what kind of common goods would be useful for all astronomers. But I would imagine that if it's like Hubble, which has done the same thing, probably 80 or 90% of it will go to individual programs, which are often done by big groups now, but we'll have different group sizes of people, small teams or things with hundreds of people, and a cycle is usually a year or a year and a half. They will have a recall for proposals, and then there are scientific panels that get together in each of the various areas of astrophysics and review them, compete them basically. And Hubble was a sort of 10 times oversubscribed telescope for all these 30 years. So hard to get time. And this, I imagine, will be the same. It's at some point where it gets higher than that, people give up. But that seems to be the point where people keep trying and actually get their time.
I realize we ignored our online audience, so go ahead, Natasha, with another.
We have an online question from Timothy. He wants to know how much more data per day will have to be transmitted and stored by JWST versus Hubble?
Oh, that's a good question. I know it was enough that it was not something, oh boy. I don't have a number, but I know that it was a challenge. It would produce these cameras can take their infrared cameras and they sort of take short exposures and pile them up, and you cannot send them all down. So you have to do some adding on orbit in order to get them compressed enough, which is unfortunate because there can be cosmic rays coming in and spoiling certain places. And if you look at, on orbit, they will try to process to see, is that a good frame? Is that a frame we should throw out? Because you won't get a chance to throw it out when it gets to the ground. But that is a problem, and being a million miles away is part of the problem. So it's a long way, and you would really need a huge antenna to get a much higher data rate, I think. But I am ignorant of the numbers.
We have a lot more questions. I see some hands up, but let's thank Al. Anybody who has a question, feel free to come up.
Yeah, please come up. Thank you very much. Thanks for coming.
There were a bunch more questions, so the people will probably come up and want to ask.
Thank you so